Okay, we just finished learning how to solve trigonometric equations. And now we're about to take a look at how to solve equations that contain inverse trig functions. And before we start this section, I want to make something clear that I don't think I made clear enough in the trig equations and the introduction to inverse trig functions sections. Okay, so as we know, when we were solving trigonometric equations, here's an example of a trigonometric equation. So we divide both sides by 2 root 3, and you get sine of 2 theta is equal to root 3 over 2 root 3, which is just 1/2. Okay, then we take the inverse sine of this entire equation, and we're left with 2 theta is equal to inverse sine of 1/2. Divide both sides by 2. Okay, and then what we would do from here is to get all possible values of theta that solve this equation, we considered the question that this was asking as far as the inverse trig function, that what angles, when you take their sine, do you get 1/2? There's an infinite number of angles that answer that question, and so that's what we listed out. So we would say, if we think about a 30, 60, 90 triangle, so 1, root 3, 2, okay, so sine of 30 is 1/2, opposite of our hypotenuse. 1/2 is positive, so sine is positive in the first and second quadrants, so we've got 30 degrees. Now, what angle in the second quadrant has reference angle 30 degrees? That's 150 degrees. Okay, then I'll put dot, dot, dot to mean any angle that's coterminal with either one of these angles, and then put divided by 2. And so the answer to this question in general is that you take 30 degrees, 150 degrees, or any angle that's coterminal with either of those two, then you divide it by 2, and that resulting angle is what would satisfy the equation. There's an infinite number of solutions. Okay, now this is kind of confusing though, because the inverse trig function, it is a function, right? It has the domains of the corresponding trig functions are restricted to create the inverse trig functions. So it's like, okay, so this is an inverse trig function. There's technically one value that corresponds to this, but we're citing like the infinite number of values that kind of answer this question. So how do we know when to think about the big picture of an inverse trig function and what the question is asking versus just thinking about the one potential, the one and only one output of the inverse trig function? Okay, and so one good way to think about this, one useful way you can think about this, and if I could remake the videos to start this chapter, I would add this point here, is that it's very similar to the way we use square roots or even roots. That's a good way to think about it, in the sense that, so we know that if you're given this, okay, someone gives you a piece of paper and says, solve this math equation, or tell me what this is equal to. They give you this just like it is. What's the answer to this? Well, there's only one correct answer here, and that's 4. That is the only correct answer. Okay, and in that context, in the same way you can think about that, if you're just given something like this, okay, like this. We worked problems like this in chapter or section 1. Well, it's in the same way as with the principal root of 16. There's only one correct answer here, because this is the inverse sine function. So, okay, root 2 over 2 is 1 over root 2. So we know we've got the (45, 45, 90 triangle, 1, 1, root 2. So sine of 45 is 1 over root 2. So this is equal to, this is positive, root 2 over 2. This is equal to 45 degrees. Or if you want to put that in radians, you could say, just put it as pi over 4. Okay, and so, but this is it. In the same way that root 16, the principal root of 16, is equal to 4 and only 4, you can look at it in the sense that inverse sine of root 2 over 2, as it's presented, is equal to 45 degrees and only 45 degrees. Okay, but now we also know that when it comes to, if we had an equation like this, someone gives you this equation and says solve this equation, just like this. Well, okay, what we need to do here is to get x, just x, we take the square root of both sides, but then we need to, well, we take the principal square root of both sides, right? That's what this symbol is. But then we need to apply the square root property, and that we need to do this, put a plus or minus here, to where what results is x is equal to plus or minus 4. And let me rewrite the equation. And the purpose of the square root property is that when we think about, we have to think about what is the original equation asking. To answer this question, the question is what value, what number or numbers, whatever, when squared equals 16. Well, we know there's two numbers that when you square them, you get 16, positive and negative 4. And so that's why this square root property is introduced for solving equations where you are required to take the square root of both sides. And you can think that there would be a similar idea with any kind of even root of both sides, but that actually, if it's like a fourth root or something, it gets a little more complicated than that, because there's certain complex numbers that when you take like certain complex numbers to the fourth power could equal a real number. So, but that was the point of like the square root property. Okay. And so in the same way, a similar way, that's what's going on here. Now, the textbook never mentioned anything explicitly like some inverse trig function property or something like that. That's why it's a little bit confusing. But really, the idea is that we started with this equation here. Okay? And then in the process of solving this, we introduced an inverse trig function. And so it's similar to that. Again, they didn't give us anything explicit about how to, like some sort of a property here, but instead of putting a plus or minus here when we took the inverse sine of both sides, it's kind of like we're asking the same question. It would be like if you said, so x squared is equal to 64. If you took the principal root of both sides, principal square root, you're kind of wanting to think about the original equation, the original question, and say, okay, well, what numbers when squared did equal 64? Well, plus or minus 8. So that's kind of why you do that. And so that's what's happening here. We're wanting to, since we introduced the inverse sign to solve an equation, it was kind of like what we were really saying was that we were really asking a question here at this step. We were asking a question of what angle or angles, when you multiply that angle by 2 and then take its sign, do you get 1/2? That's what we were asking. So in that sense, we were just using the inverse sign as a tool to get to that answer. So we took the inverse sign, but then we needed to think about the big picture at this step and list out all of the angles. You see? And so with that, we're about to start equations that contain inverse trig functions. Okay, so if you have something like, if you're given something like this, okay, you're given this, it would be like the same idea as if you were given, you know, x squared minus 3 is equal to the principal root of 64. If you were given this equation, how would you solve this? Well, you wouldn't do, you don't say this. That's not correct, right? This as it sits, this is just 8. Then you add 3 to both sides. Then you would take, that would be the answer, right? And so when we look at an equation like this here is just a single number. This here is just a single number. So, you know, the easiest thing to do would be go ahead and turn this into a number. So, okay, the question is, what number or what angle when you take its cosine do you get 5/13? That doesn't fall under any of the special angle categories, so let's go ahead and just use the 67.38. So we've got, and that's it. That's it. You know, the range of the arc cosine is 0 to 180 degrees. It's in the first quadrant because it's positive, so that's it. That is the one and only answer to this. What's on the right side? Okay, now how would we continue to solve this? Well, we know that when it comes to functions and their inverses, functions and inverses are inverses of each other. So the inverse of the sine function is arc sine, but then also the inverse of arc sine is sine. That's a property of inverses and their functions and their inverses. They're inverses of each other. They go in either direction. So if you take if you take the tangent of x, to undo that, you could take the arc tangent of that. So, okay, if we start with x and we take the tangent of x, now if we want to undo what we just did, we can put this into arc tangent, and now we undo that. We get x back. Or it goes the other direction. If you took x and you took the inverse tangent of x, if you wanted to undo that, you put that into the inverse of inverse tangent. That's tangent. And you're back at x. So we can take, to solve this here, we can take the tangent of both sides of this equation. So tangent of arctangent of x is equal to x. And then we've got tangent of 67.38. Well, this would be in degrees. Okay. But now, we introduced the tangent, right? We introduced that. So do we need to take a step back and think about a bigger picture here? Well, no, not in this case. We don't, because we know that just their original trig functions over all the entire domain are actually functions. Like the inverse trig functions, they are functions, but they came with that restriction involved, which means that if you introduce it, if you introduce an inverse trig function, you can step back and think about the bigger picture. Well, when it came to actual trig functions, there was no domain restrictions or anything. That they just are what they are. So there's only anytime you have a trig function, you're evaluating a trig function of an angle, there's only one value to that every time. So we just, okay, take the tangent of this, 2.4, and that's it. You see? And so in that sense, if I could go back to section 6.1 where we learned about the inverse trig functions, I would have liked to have been more explicit and explained this clearer in that. So every time we went through problems like this, we would give the answer, but then I would say, well, but it's common practice to always think about the bigger picture every time you take an inverse trig function. And that is kind of true in the sense that's what I found, that it's a lot more common that when you're dealing with an inverse trig function, that you're usually going to be always thinking about the bigger picture of in most scenarios where you're using an inverse trig function, you're thinking about that bigger picture. If you're working an engineering problem, etc., it's usually the case that you want to think about the bigger picture of the different values that answer the question, as opposed to, it's not as common to always have to think about every time you take a square root of something. You're thinking about, oh, well, is the negative value applicable here? So, but still, though, as we get into equations that contain inverse trig functions, it's going to be really useful to understand what I'm talking about in this video. Okay, so like an equation like this, we're presented with arc cosine of something. We're thinking about this as the arc cosine function, not all of the different possibilities that could come out of that, that answer the question, what angle when you take its cosine, you get x minus pi over 3. No, we're thinking about this as an actual function now. Okay, and we'll learn how to solve equations like this in the next section.